We have already explored the incredible power of using f-string syntax, so here you have a username variable and a points variable, and what you want to do is print not just the values of these variables, but also the actual name of each variable itself. All you need to do is add an equals sign right after the variable name, and watch the output show username equals James and points equals 185. Now, the reason this syntax works is because Python says print the expression exactly as written, so username, and then follow it immediately with its value. Whatever the value of that expression is, it gets printed. In this case, it is a variable, so it outputs its value of James. That is all there is to it. To show you another example, you can do something like this. You define x and y, and inside the f string, remember to include the letter f at the very start of the quotation marks, otherwise this will not work. So you write x plus y followed by an equals sign. Now notice that equals sign. What it does is output the full expression information like this. X plus y equals 13. So 10 plus 3 gives us 13. You can see it prints everything before the equals sign, and you can prove it by removing the space here. Notice how the space is now gone from the output. Add the space back, and Python evaluates the expression and prints it exactly as written, and then shows its value, the result of the expression. Now, if you do not want Python to evaluate the expression, simply remove the curly braces, print it like that, and you get the raw output without any evaluation. But as soon as you put it inside curly braces, Python will evaluate the full expression x plus y. And you can also do even more, like printing the expression for price, where you can get the output formatted in a very specific way. For example, here you can see we are formatting it to 2 decimal places, and the formatting specified after the colon still works perfectly. So essentially, the left side is the value, and because it has the equals sign, Python will evaluate it first, and then after the colon, it will format the result to 2 decimal places. The same principle applies throughout. Print whatever is before the equals sign, evaluate it, apply any formatting. This is a brilliant shorthand for debugging. And here you can see that 42 gets padded to a total length of 8, meaning the number 42 is followed by 6 zeros. And this is what is actually happening behind the scenes. Python is using the representation of username, which is why you see single quotation marks in the output, because Python is using the representation function internally. If this video has helped you understand the f-string syntax, how it works, and what you can do with it, please give it a like, drop a comment, and follow and subscribe to get more videos just like this. Let's explore the critical difference between double equals none and is none. The best practice is always to use is none, because this checks against a truly empty or non-existing value, while the double equals sign performs a comparison. So let us look at an example. Imagine there's a class in your code that stores employee information. It stores an employee ID. When you create employee 101, that employee ID gets stored. Then when you check if employee 1, which has ID 101 equals none, the output you get for that check is false. That seems perfectly correct. There is definitely an employee 101. This is clearly not none. There is data there. But here's where it gets really interesting. For employee 2, look at this. When we run a double equals none comparison, the answer comes back true. So why does it return true? That is exactly why. If you look at the second check using is none, it correctly identifies it as false, because there is an employee with ID 0. So what is actually happening with double equals? This is precisely why Python recommends using is over double equals. With double equals, a developer can actually override and redefine the behavior of that double equals sign. So they can say here, if the other value being compared is none, that none value flows into this parameter here. And then they say, if other, the value passed in, is none, then return whether the employee ID equals 0. As soon as that triggers, it returns true, because the employee ID is 0, making the none comparison return true. So the developer has overridden the behavior of double equals, but they cannot override the behavior of the is keyword, because saying employee 2 is none returns false, since there is an employee with ID 0. So why has this happened? Because internally, the developer decided that when the employee ID equals 0, it should be treated as equivalent to none. That is why they overrode this behavior, incorrectly so. But you will encounter this pattern in real code bases. It happens. That is why, to truly check for missing or non-existing values, you must always use is none. I know it is difficult to find a perfect example of this, but I hope this clarifies why is none is safer than double equals none. Just think of it this way. Double equals behavior can be changed. That is the simplest way to remember it. With double equals, anyone can make employee 2 look like none by simply overriding the behavior. Look, you can see the if condition here, and they could simply return true, or run some kind of custom comparison. They could even just do this to get the same result. They can literally return true, and it would still work. That is the key takeaway here. Double equals behavior can be changed, while as none behavior cannot be changed. The taser's keyword checks for the genuine non-existence of a value, and that behavior of the taser's keyword is locked, unchangeable. In Python, you can create a class and assign it dynamic properties on the fly. This means your class can start completely empty. Here, we are going to create a class called dog, and the keyword pass here means this class does absolutely nothing yet. It is simply a placeholder. Then you create a variable called dog1, and inside it, you initialize an instance of the dog class. We initialize it right here. And since the dog class has no predefined properties, you can dynamically assign properties and access them later. So here, for example, you're creating name and age, and those are being added dynamically at runtime. And you're able to access them just as easily. Python allows this remarkable behavior, which is actually quite unusual compared to many other programming languages out there. Let's dive into the anatomy of a basic Python class. A class is the blueprint you use to manufacture objects. Think of it like a recipe that lets you create a specific dish over and over again. In this instance, let us say we have the DNA blueprint of a dog. We can essentially clone a dog from it. A dog will always have a name and an age. That is the blueprint. This is the blueprint. The dog's DNA says it will always have a name and an age. And then when you create an instance from it, dog1, you get a dog named Buddy, aged 4. When you print the name of that dog, it prints the specific dog that you created. So here we get Buddy and 4. Now, what is happening behind the scenes is that on this line, you create an instance of the dog by calling the dog class initializer method. In that initializer, you pass in the name Buddy and the age of 4. Inside the init method, you receive self, which will be the dog1 object itself. So self is dog1. The name flows into this parameter here, and age flows into this one. You might be tempted to think you have to do it like this, passing dog1 explicitly, like in this fashion. But running it that way actually fails, because explicitly passing it is wrong. Dog1 gets passed in automatically by Python, right? So when you call this initializer, you do not pass dog1 yourself. It gets passed automatically. Dog1 arrives here as self. The name maps to this parameter, and age maps here. You only need to supply the values for name and age. Self gets handled automatically, right? So do not worry about that part at all. And once you assign the instance, you can directly access the name and the age of that dog. Now, there is something else interesting. You can actually sneak in extra attributes. For example, on dog1, what we will do is add a city attribute and set it to London. Python does not complain at all, and you can access that new attribute right here. You can see, I can access city. And if I print it, the output is London. So we are able to dynamically add properties to an instance in this way. But this is generally not recommended, because imagine you have a dog 2 and someone misspells city or accidentally writes city with 2 T's instead of city like this. You end up with a real problem. So when someone creates dog 2, for example, I set it equal to the dog class and name the dog Charlie. And we give it an age of 5. When you now access dog 2, you can see the only attributes available are name and age. There is no city attribute on dog2 at all. Can you have private attributes in Python? The answer is yes and no. You can, but they are not truly private. Let us take a look at this example. Here we have a bank account class, a blueprint for a bank account. An account can have an owner and a balance. Those are the 2 properties defined in this example. The first account we create is for James. James is going to start with a balance of 1,000. You can then query who the owner is and what the current balance is. You can print that out directly. But the problem is, I can come along from outside the class and change James's balance directly, just like this, set the balance to 2,000. The code happily changes the balance to 2,000 with 0 resistance. That is where the underscore comes in. A single underscore prefix signals it is a private variable. It should not be modified by any code outside the class itself. There should be checks and controls, because someone could accidentally set the balance to -2,000. Or they could mistype and enter a balance of -999, and it still goes through without complaint. There are no checks or validations in place whatsoever, and they could do all sorts of ridiculous things like this. Nobody should have a balance like that sitting in a single account. So Python gives you the double underscore prefix. Here we use a double underscore. Now, when you try to modify James's balance externally, you get an attribute error. Python tells you there is no field called balance, even though it is right there with the double underscore prefix. What is actually happening is Python is making it deliberately harder for you to tamper with private variables. But unfortunately, or fortunately, depending on your perspective, you can still access it if you really want to. All Python does is rename it. Using a technique called name mangling, you can see right here that it renames the field to underscore, followed by the class name, then double underscore balance. So you can still reach that attribute if you know the trick. So if I comment the first line out and run this, you can see it still works. This does mean you can still modify the balance this way and put anything you like in there, and it would still go through. So it is not true protection or genuine security for private variables. It simply makes tampering significantly harder than the single underscore approach. The best practice in Python is to ensure that any attributes or properties of a class that should not be touched by code outside of it are declared with a double underscore prefix. What this allows you to do, for example, is create a controlled bank account. Let us say this account belongs to the owner James. The value you pass in here gets mapped to the owner, and the balance value gets mapped to the balance variable here. Once the account is set up, you can retrieve the balance by calling the getBalance method right here. This method returns the double underscore balance field. Running this code, you can see we get a balance of 1,000. Then you can make a deposit. The deposit executes this function here. With the amount passed in, if it is greater than 0, that amount gets added to the balance. To block negative numbers, if you try depositing -500, the balance never changes, it stays exactly the same. But as soon as you deposit 500, the balance updates correctly. And you can see the getBalance method outputs the updated balance right here. Now, the double underscore balance field is still directly accessible, as I have demonstrated here by printing its value. So it is not completely secure, because you can still reach that field like this. For example, I can do this and force the balance to 3,000. Running the code, you can see the balance has jumped to 3,000. So the user has essentially bypassed the deposit method entirely and directly manipulated the variable. Python allows this, unfortunately, but it does make it harder because the balance field inside the class itself is referred to simply as double underscore balance. But from outside the class, you have to go out of your way and write bank account, the class name, then underscore bank account, then double underscore balance. So this is not truly a private field or attribute. It is still reachable, but with a meaningful extra effort. So you should use the official methods you declare in your class to interact with these protected variables the right way. Let us explore the key difference between class variables and instance properties versus instance variables. This one is really important. Here we have employee1 and employee2 variables. Using the employee class, we are going to create one employee called James and a second employee called Sarah. Then we are going to print out their details. We will print employee 1's name and employee 1's company. Now notice the company is declared at this level here. It does not use the self.name syntax. It is just a standard class level variable in Python. When you run this code, you can see the output shows James as the name of the first employee, and Sarah over here for the second employee plus the company. Now, look at this section. We are going to change the employee company to NewTech and change the employee to name to Emma. What do you think will happen? Will it change the company name for both employees? And what about the name? Will that change too? Will the name update to Emma? And will that affect employee 1 as well? Running this code, you can see James remains, but the company has changed to NewTech, as we defined here. And for Emma, which is now employee 2, but where did Sarah go? Sarah has been overwritten by the name change here. But this did not affect James because name is an instance variable. It is an instance variable being used here, while company is actually a class variable that affects all objects of that class. So company is shared by both employees, while name is unique to each employee. By using self.name, you are declaring that it is an instance variable rather than a class variable. One critical thing to watch out for with class variables is that you can accidentally shadow them without realizing it. What I mean by that is, we have an employee class here, and it has a class variable called company, and an instance variable called name. When you create employee James and employee Sarah here, and then you write employee1.company equals Google, what is actually happening is you're creating an instance level variable because you're referring to the specific instance here, employee1.company. So Python will go ahead and create a brand new variable at instance level called company and assign it the value Google. Now, because there is already a class level variable, Python will shadow it and use the instance level 1 for employee 1. So when you run this, you can see employee 1's company has changed to Google. Employee 2's company is still Tech Corporation. And the class level company is still Tech Corporation. Instead, what you should do is call this using the class name employee and change the company to Google. Running this now, you can see employee 1 is Google, employee 2 is Google, and of course the class level is also Google. So avoid doing it on the instance, because that will shadow and override only the instance variable, leaving the class level 1 untouched. I hope this tip helps you understand class level variables versus instance level variables, and the shadowing behavior that occurs when you name an instance variable the same as a class level variable. The instance level variable basically wins and shadows the class level variable for that specific instance. If this helped you, please like, comment, and subscribe, and follow for more videos and tips just like this. If you want to track the total number of objects being created from your class, you can do that elegantly using a class variable. This class variable, employee count, starts at a value of 0. Then every time a new instance is created, inside the init method, the initializer, we assign the employee's name, James, Sarah, David. James, Sarah, David. But then at the class level, notice this line here. This is class level code. Employee is the class name, and we increment the employee count by 1 each time. So every time an object is created, when James is created, it starts at 0 and adds 1. That gives a count of 1. Then Sarah is created. The count becomes 2. Then David count is 3. To show you this in action, what we will do is print the count after each object is created. Then you can watch it live in the output. Running this, you can see James is created and the count is at 1. Then Sarah count is at 2. And David count is at 3. So the class variable accurately tracks how many employees have been created using the class variable right here. Just remember to reference it as employee.employeeCount. Always use the class name to increment the count. And you will always know exactly how many objects exist for that class at any time.